Not quite. They each have their own meanings, but they are related. So what's global warming? We have seen an increase in the surface temperature averaged over the whole globe over the past century and a half, and that temperature continues to rise. NASA has analyzed data about the Earth's climate system from multiple sources that tell the same story. On a global scale, the Earth's surface is heating up because of the increasing amounts of heat-trapping greenhouse gases that have been released into the atmosphere from humans burning fossil fuels. That's global warming. Climate change is a more general term. It also refers to long-term changes over many decades or hundreds of years, but it includes all types of changes in the typical weather climate that can be and have been observed from regional to global scales. NASA has instruments that have observed a diverse collection of the current impacts of climate change, like decreases in ice in the Arctic, droughts, increasing wildfires, and increasing surface temperatures. These are all examples of indications of climate change. So is climate change the same as global warming? Not quite. They have their own specific meanings, but they are related to one another.
So the question, where does space begin, it depends on your point of view. You could really ask, where does the atmosphere end? And as you think of the atmosphere where we live and breathe here on Earth, it doesn't just stop right above our heads. It doesn't stop at Mount Everest. It doesn't stop where the planes are flying. It goes on and on all the way up and just gets less and less dense the higher you go. And it's still there at a very high altitudes. When you go to where the space station is, only a couple hundred miles above the Earth, there's still enough air there to slow the space station down. And if you didn't reboost it with rockets, it would come back to Earth based on the air drag, just like when you're driving your car. So that region up there, even though it's not like what we're used to here, you couldn't breathe there, there's still enough atmosphere there to make it interesting. Not only is there air like we have on Earth, there's ionized gas, there's radiation. All those things together make that environment really dynamic and has something we call space weather. And in a sense, we live in the atmosphere of the sun. So there's this kind of dichotomy there where you go from the Earth's atmosphere, then you're in the sun's atmosphere, and then at some point you're outside that when you reach the heliopause and the heliosphere boundary. So if the question is, where does space begin? It depends on your point of view. If you want to know where does the atmosphere end, it's about 400 miles over your head. But just remember that that space above that is not empty. It's full of all kinds of interesting stuff. And that's what we study at NASA.
Yes, definitely. But on other worlds, these aren't called earthquakes, they're called moonquakes or Marsquakes if they're on the moon and Mars. We know that these exist because we actually sent seismometers to the moon and to Mars. And when we sent seismometers to these worlds, we actually found thousands of quakes underneath the surface. Even when we don't have seismometers on other planets, we can actually tell that some worlds have earthquakes or had earthquakes in the past because there are cracks of the surface. And so when we see cracked rocks or even cracked ice on places like Europa and Enceladus, we know for a fact that there were quakes there to generate those cracks. Quakes of all sizes are really interesting, and they can tell us a lot about the inside of a planet. Bigger earthquakes, bigger Marsquakes, and bigger moonquakes can tell us about really deep processes and features on these planets. Now, recently, we've discovered that the moon also has a small liquid core surrounding its solid core, and we've also discovered, thanks to NASA InSight, that the Mars core is actually larger than we initially thought, which means it's actually less dense, which is a really interesting science puzzle. So understanding the interior of other worlds will help us understand how our own world, the Earth, evolved. So are there earthquakes on other planets? Definitely. Moonquakes, Marsquakes, and possibly one day we'll be able to send seismometers elsewhere to record Europa quakes and Enceladus quakes and beyond.
No, NASA is not mining asteroids. The technologies for mining asteroids are not well developed. We actually can't really mine asteroids yet, although many people are working on it, private sector, people outside of NASA. What NASA is doing is fundamental science, research missions that go out to asteroids to try to understand more about them, and they will help any eventual future efforts to mine asteroids. And our NASA Psyche mission is an example of one of these missions. We are going to visit an asteroid that we think is made largely of metal, but from those pure science missions comes the information that maybe in the distant future, humans will be able to mine asteroids and save some of the resources on Earth. So is NASA mining asteroids? No, but NASA is doing the fundamental science of sending missions to asteroids to understand what they're made of.
Well, actually, we don't know, but even trying to answer it is super fun because it takes us to like all these crazy imaginative places and environments. Some people think it started in hydrothermal vents at the deepest, darkest, warmest parts of the ocean. Some people think it created in these little ponds that material is collected and concentrated within. And other people think it maybe formed in environments that were a combination of those things, like maybe a big impactor came in from space and made a pond with a vent at the bottom of it. And part of how we research this is by looking at those environments, the wild places that could have existed on early Earth that led to the formation of life, the chemistry that's required for life to have originated, and then also thinking about what life is in the first place and what life requires. At NASA, we fund the chemists and the geologists and the astronomers and the planetary scientists that you need to bring to the same table to answer those questions in detail. We do that through NASA's astrobiology program. And we incorporate thinking on how life originated or could originate elsewhere into our missions and our planning to look for life on planets beyond Earth, whether that's on Mars or in the ocean worlds of our outer solar system, or with big space telescopes that can look for signs of life on planets around other stars. So how did life begin on Earth? We don't know, but we're working on it because it's important both to the story of here, our history of life on our home planet. It's important also for our search for life beyond Earth and answering the other question of are we alone?
There aren't many classes of objects left in our solar system that we haven't looked at up close with a spacecraft. And one of them that's left is the metal asteroids.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
The reason that Psyche is unique is that it is metal-rich.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
This is the part of planets that we can't sample directly today.
It's too hot, the pressure's too high, our instruments would melt. Can't drill a hole that deep in the Earth or other planets. So how do we study the core of our planet?
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
After launch, we cruise through interplanetary space for a number of years. First, we fly by Mars for a gravity assist that'll slingshot us into the asteroid belt. And then we're thrusting all the way from there to finally arriving at Psyche.
We'll go into 4 orbits to collect the necessary measurements that we need from our 3 primary instruments.
So our payload consists of a couple of imagers, which are cameras that take pictures of Psyche. Also a gamma-ray neutron spectrometer, which allows us to measure the elemental composition of the surface of Psyche. And then a magnetometer, which will allow us to detect any magnetic field that's left at Psyche.
If Psyche still has some sort of remnant magnetic field, that probably tells us it really was a core. It's a strong indicator. We also use the radio on the spacecraft as an instrument, so we can map out the gravity and map out the interior structure that way.
We're using a particular thruster technology, Hall effect thruster technology. They operate 5 times more efficiently than normal rockets, so they use a lot less fuel, and is what allows us to get into orbit around this asteroid.
Solar electric propulsion has been around for quite a while, and it has flown before, but we're continuing to push the boundaries. We're going to have big 5-panel fold-out solar panels that will provide the electricity for the thrusters, which use as propellant the noble gas xenon.
This will be the first time that Hall effect thrusters have flown in deep space.
Studying the evolution of a planetary body is a detective story.
There's a magic, too, when you actually are on the launch pad and you say, we're go for launch.
And you feel like singing and dancing and you feel like throwing up at the same time.
Let's go discover things about our solar system that we have no other way to do. I think that it's fundamental to who we are and also who we should be. It's an incredible opportunity to be a part of the team making that happen.
So they used to be a huge problem, and because of that, there was a hole, especially in the Antarctic, in the ozone layer. Ozone works as Earth's natural sunscreen. It prevents harmful UV radiation to come down to the surface to cause skin cancer and damage vegetation. Man-made substances such as chlorofluorocarbons, because they were so safe, they were used in a variety of applications such as refrigerants or insulation foams. These gases have very long atmospheric lifetime and can find their way into the stratosphere. When up there, they can decompose and release chlorine and bromine atoms and destroy ozone. Although there are ozone-depleting gases everywhere in the atmosphere, the ozone hole forms in the Antarctic because of the special weather conditions there. The very cold temperatures in Antarctic can form ice clouds called polar stratospheric clouds. Special chemical reactions can occur on these clouds and destroy ozone and form a hole in the Antarctic during spring. The ozone-depleting gases have been regulated by the Montreal Protocol, which is an international agreement signed by all countries around the world. Because of this, their levels in the atmosphere has been decreasing. As a result, in recent years, the ozone layer has shown first signs of recovery, although there are still large year-to-year variabilities in its size and strength. But the whole world has worked together effectively to reduce the problem, and because of that, it is projected the ozone layer will recover and return to a healthy level by mid-century.
So if you stick back in time, thousands of years ago, people knew about the brightest planets pretty much everywhere. These are Mercury, Venus, Mars, Jupiter, and Saturn. Pretty much every culture knew about these 5 planets, which they could easily see up in the sky. They had different names for them, the names that we use now in English. These come from the Roman names. And that's because the early astronomers in Europe wrote in Latin. And Latin was the language of the Roman Empire, so we ended up with these Roman names after the Roman gods: Mercury, Venus, Mars, Jupiter, and Saturn. If we keep on going outward, we have 3 more things that historically have been called planets. You have Uranus, Neptune, and Pluto. These are Greek or Roman names. These planets weren't seen by the Greeks or Romans, but because the discoverers wanted their planets to fit in with the existing theme of the mythology of the existing planets. And all these are totally different than the inner planets because these were discovered more recently. They're fainter and they move more slowly. You can't see them with your naked eye. You have to use a telescope, and that's how they were discovered. But since then, as telescopes have gotten bigger and bigger, astronomers keep finding smaller and smaller things in the solar system. And we discovered some things that are just a couple of meters across, like literally the size of a person. And we've discovered thousands of Kuiper Belt objects, which are more or less like Pluto, a little smaller, a little further away, but the same basic idea. Some people still call it a planet, but oftentimes it's called a dwarf planet. That's what the International Astronomical Union says, is the group responsible for naming things. The issue with Pluto is you're trying to define a fuzzy line between a planet and not a planet, and it boils down to size. So there's so much more in the solar system to name. There's moons, asteroids, comets, rings, Kuiper Belt objects, craters. Because we're humans, we want to name these things. It gives us a connection to the huge universe around us. Thousands of years from now, people are still going to be naming planets as we continue to explore the world around us.